All right. Well, hello, everyone, and welcome to the first Tech Industry Luncheon talk of 2022. My name's Rod Wetterskog. I'm the Assistant Dean of the Johnson School of Engineering and Computer Science at the University of Texas at Dallas. And I'm also a member of the Tech Titans program team that plans these monthly Tech Industry Luncheons. It's my pleasure to MC and moderate today's program. We're glad you joined us today for what should be a very exciting discussion about quantum computing. And the program's team's excited to again welcome the UT Design program at the University of Texas, Dallas, as our presenting sponsor of the Tech Industry Luncheon Series for all of 2022. And for a few words about the UT Design program and UT Dallas, please join me in welcoming the Director of Corporate Relations for the Johnson School of Engineering and Computer Science, Don Prochel. Don, take it away, man.
Well, thank you, Rod. Good afternoon, everyone, and happy Friday. We're less than a week away from the start of the Winter Olympics, with athletes competing for gold medals and world records. This spring, our gold medal caliber UT Design Capstone program launched a world record 90 computer science capstone project teams, providing innovative solutions to their company sponsors, with the vast majority of these sponsored by North Texas companies. We have over 6,500 undergraduate students in the Johnson School, and our entering freshmen average 1420 on their SATs and include over 100 National Merit Scholars. These incredible students get to build their engineering solutions in a world-class design studio, supported by an all-pro team of faculty, directors, and support staff, key reasons why our student teams have won 9 national championships since 2014. We welcome companies of all sizes, from startups to giants like Raytheon, State Farm, Corvo, Murata, and TI. These corporate sponsors have learned that we can give them a team of up to 6 capstone students for less than the cost of 1 intern. They have 1 or 2 semesters to try out these students for possible entry-level positions in their companies, all while working down part of their project backlog that they otherwise might not be able to address. We are right now signing up sponsors for engineering capstone projects to launch in May for our summer semester. So contact me for engineering projects, or our other corporate relations team member, Cynthia Hine, for computer science projects that will launch in the fall semester. I'll put our contact information in the chat window. For more information about UT Design Capstone, visit our website at www.utdesign.com to learn how our students can accelerate your company's success. Let us be your engineering force multiplier. Back to you, Rod.
Thanks, Don. Boy, Don, I feel like you need to get a commercial during the Super Bowl halftime show. We really appreciate Don and the UT Design Capstone program being, again, our 2022 sponsor. The 2021 Gala, Tech Titans Gala, was last Wednesday. And man, was it quite the show. Even despite the COVID restrictions, over 200 folks were there, had a great time. The 2022 Tech Titans Award nominations will be opening next week. So please make sure that you reach out to those that you know, those that you believe are worthy of this tremendous honor, and start pouring those nominations in. A quick reminder that the Tech Titans Luncheon returns to its traditional third Friday of the month on February the 18th. We're going to host 3 CIOs from across the country in a salute to Black History Month. We're going to have Michael Peggees, the CIO of the city of Aurora, Illinois, Onyeka Nichegu, the CIO of Novent Health in Atlanta, and Tanya Hanna, the CIO of King County in the state of Washington. They'll be sharing their stories of how they climbed to the positions of CIO, along with their views on current technology trends. Now, currently, we're planning that program will be presented virtually, but please watch the Tech Industry Luncheon webpage and the Tech Titans website and the weekly event calendar for updates. Now, before we introduce our speaker to you today, you're reminded to please put your questions in the chat function of the Zoom call. Paul, Mallory, and I will be monitoring those, and we'll ask your questions during the Q&A session to Simone. Our program today is about quantum computing. It's a type of computation that promises to solve some problems that are currently beyond the reach of digital computers. Quantum computers perform these functions more efficiently and at a greater speed with qubits. Quantum bits are used to perform the calculations. Now, there are many unknowns that remain, such as how should we build such a machine so that it can handle big problems, useful, practical problems? How can we scale it to thousands and millions of qubits while maintaining precise control over fragile quantum states and protecting them from their environment? And what custom problems should we design this new technology to tackle first? And what's the timeline? We're delighted to have Simone Severini of AWS with us today to answer these questions and show us how this amazing technology works with some best use cases. As Director of Quantum Computing, Simone's responsible for designing and delivering the strategy of Amazon Web Services in quantum technologies. He contributed to bring to life AWS's effort in this space, including Amazon Bracket, the quantum computing service, the AWS Center for Quantum Computing R&D organization, and the Amazon Quantum Solutions Lab. Simone's also a professor of physics of information at University College London, where he helped to start the UCL Quantum Science and Technology Institute, along with industrial partners including Google, Lockheed Martin, and Siemens. He held several advisory roles in the public sector, the private equity funds, and helped some of the world's first quantum technology startups. Now, here's a factoid about Simone that will be interest to any students out there. Simone will tell you that he's not good at math. He never has been, not in school, not at Amazon, and in fact, he feels inferior when, imagine the guru of quantum computing at AWS ever feeling inferior when he thinks about his math skills. Yes, he's co-authored over 100 papers with mathematical content while working in this science area, but still he admires people good in math, knowing that they have the ability to control their thoughts and reasoning using mathematics. Now, this is his quote: "When I do math, I feel like I'm swamped in a lake of mud." So to those of you that are thinking about a STEM career and you don't think you'd be any good at it because you're not good at math, wait till you hear from Simone. Remember, put your questions in the chat function of Zoom, and let's now learn the 10 things we need to know about quantum computing. Please join me in welcoming Quantum Computing Director of AWS, Simone Severini. Now to you, Simone.
Okay, so can you see my screen?
Looks great.
Yeah, okay, great, thank you. Thanks for the kind introduction, really. It's a privilege to present in front of this audience. And thanks to the organizers of this meeting for giving me the chance to talk about a topic that I feel very close to my heart. And the title of my talk is Questions about Quantum Computers. So you have most probably noticed that I changed the title of the talk with respect to the title that I submitted originally. I think that this title is better, it's shorter, and it sticks better to the mind of people. The talk will be a list of questions with some answers. And these are questions that often people out there ask, like customers, for example, or people reading stuff on the internet about quantum computing when trying to determine what is real and what is not about quantum computing. But these are also questions that I ask myself. So I thank the organizers once more, not just for the kind invitation, but also for the opportunity that they gave me to think more deeply about quantum computing while I was preparing this talk. So I wish that we had the opportunity to be in the same room, and I hope that I will meet in person some of you in a not too distant future. And so please notice that I added my academic address on this slide under my name. So please do feel free to email me if you have any specific questions. and I will try to answer or put you in touch with people that that are more expert than I am, and that can potentially give you an answer in case I won't know the answer to the question myself. Now, the very first point that I would like to talk about, the very first question is, what is quantum computing? So usually general talks about quantum computing give a number of definitions that come from physics. They start with the notion of a qubit, which is the fundamental unit of information for quantum computers, and it's the quantum analog of the bit. So then they tell about phenomena like entanglement, about interference, about parallelism, and of course, about how interesting quantum computers are in solving important problems. Now, this talk will avoid discussing these technical topics, and it will be an overview which does not involve technical material apart from a few lines on this slide only. So the talk will be around the idea of quantum computing, why quantum computing is important, what is not quantum computing as well, what is its impact, and how you can engage with the technology. And the first point to give attention to is that quantum computing uses and it involves quantum theory. This sounds a bit self-referential, tautological, but it's fundamental. Quantum theory is a physical theory, meaning a set of statements about our physical world, which turns out to be very successful in describing and predicting the behavior of experiments that have to do with small objects. Small objects are objects at the macroscopic scale, at the nanoscale, like atoms, for example, or photons, which are the components of light. Now, quantum theory is very unintuitive, and I use the term unintuitive rather than counterintuitive. Why? Quantum theory, it's hard to picture in our mind. It's hard to picture how it works, and not least because we don't experience quantum theory with our senses. In the world around us, we don't touch or see quantum phenomena, at least as far as we know. But this theory, for the ones among you that are familiar with probability theory, reminds a bit of probability theory, but where events are associated to have associated probabilities that namely could have a negative, that namely could be negative. Of course, probabilities usually are numbers between 0 and 1 in quantum theory can be negative. And this is important because quantum objects behave like waves, and these negative numbers can create destructive interference and interesting phenomena associated with that. So first point about quantum theory, just two keywords: negative probabilities. So the second point is that in quantum theory, and this is fascinating, the observer, when she runs an experiment, she modifies the state of the object that she's observing just by interacting with the object itself. And this is counterintuitive. But why? Because it's almost like if the observer creates a reality while observing the world. And the third point is important, is an important intuition at the basis of quantum computing. If you want to study with a conventional computer, a digital computer, the behavior of quantum objects out there, it's very time consuming. It takes a lot of computational power to do that. But then why don't you try to study quantum objects with quantum mechanics itself, with machines that use quantum mechanics? Now, something that I really like is that quantum computing is both a science and a technology. Science, because it's an opportunity to study how nature works at the fundamental level through the lens of computation. And it helps exploring the ultimate physical limits of computation. But it's also technology because it has to do with building machines and ways to operate machines. And these machines are called quantum computers, machines that are governed by the laws of quantum theory. And they function in a way, and I say this very informally, in a way which is deeply different from computers that use the physics around us, the physics of Newton, which is the physics used by all other types of computers. And the steps of a quantum computation would consist of a sequential manipulation of physical state of some quantum objects, like atoms, for example, and then an observation at the end of the computation to read out the result, which is going to be then probabilistic. And please don't be alarmed if this slide is somehow technical. The rest of the talk won't go into anything technical at all. But one remark to be made is that quantum computing is part of a broader set of technologies called quantum technologies. And I won't talk here about this broader set. I won't talk about quantum cryptography, about quantum sensing, or about quantum communication. So I will stick to quantum computing. Now, let me go to the next slide. So this is slide number 2 and question number 2. Why is quantum computing important? So to me, the most important aspect of quantum computing is that it creates an interplay between computer science and physics. I know it sounds abstract, but I like this view. It helped growing the idea that computers are actually physical objects and that obeys the laws of physics. So, and the laws of computation, even if it seems abstract, can also be considered as part of physical reality. And this teaches us a lot about the world in both directions. And I'm not talking about computational physics. I'm not talking about computers to figure out like physics is how to compute, but I'm talking about a new discipline that embodies both physics and computers. And even from the theoretical point of view, these two disciplines now influence each other, and which is beautiful. For example, one could claim that a computational problem would be easily solved if a certain physical phenomenon potentially occurs in the real world. But then, if that problem cannot be plausibly solved easily by a computer, then maybe that phenomenon is not really real. And quantum computers are then machines really to explore nature in first instance, like telescopes, imagine, or like particle accelerators. And the opportunity is that we can handle let's say the concrete opportunity that reflects into business is that we can handle some problems beyond what conventional computers can do. Now, conventional means non-quantum, or a term that is routinely used in the scientific community is classical. So when a computer is not a quantum computer, it's called a classical computer. So, and what does it mean beyond classical computers? So quantum computers are faster for some problems, meaning that they give the solution sooner. And we should not forget that when you run a computation, you need to wait. You need to wait for the answer, right? And we should not forget that there are some problems out there that could take millions of years to be solved on a classical computer. But putting on the side the computational speed up, I want to stress once more that quantum computers are machines that could impact science and technology profoundly. And this is not a statement about some incremental gain only, like a faster computation. It's deeper. It's not just about saving time, but about doing things that we cannot do without quantum computers, like accessing a layer of reality that we don't experience ourselves and that we cannot explore unless we have quantum computers. And here is my third point. Point 3, what is not quantum computing? So I know now this sounds a bit of a weird title for a slide, but you see there's so much hype out there now about this topic that it's really hard for the general public to get a sense of what is real. And we need to be aware of some widespread misconception. And you know, why we should be aware, not because we want to be adversarial in any form, but because a discipline that until not long ago was mostly scientific and academic, now that it entered industry, is partly and physiologically filled with noise when it comes to communication. So first point, quantum computers have atomic scale components, have small components, but quantum computers are not smaller. They could be huge. So it's not about miniaturizing a computer. They could fill entire rooms, for example, right? In fact, today they do. So second, I said that quantum computers could potentially solve some problems faster than every other type of computer, but this does not mean that the single fundamental operations are faster. This means that the number of steps of the procedure of the algorithms that they implement are going to be less. And so is the procedure that is faster, not the execution of the single steps. And third point, quantum computers are not a kind of magic bullet, a panacea, that something that can cure every illness, right? Meaning there's a lot of computational problems out there. There is strong scientific evidence that quantum computers will speed up only some of these many problems, and there are the problems will remain hard. Maybe we can shave a little bit of complexity, but they will remain hard. And fourth, to build quantum computers, we need quantum theory. We need quantum systems. When people say we have a conventional computer that is identical to a quantum computer, it has the same thing, but no, it cannot. And there is scientific papers that prove that. So the final point, maybe here is the more sticky one. So today, quantum computing is a nascent technology, is in R&D phase, is accelerating, is exciting. I'm very excited about quantum computing myself, but today quantum computers have not been yet demonstrated to bring any advantage to business problems. The quantum computers available today, of course. And quantum computers, however, are stimulating a lot of conversation. I think that this is important, but not yet impacting business. And I hope that they will have an important role in business, but the role has still need to be demonstrated. And this does not diminish in any way the importance of quantum computers, because as I mentioned, quantum computers are already a tool for innovating, and to some extent, people that are operating quantum computers today and thinking about quantum computers, they are innovating even in business, even if there's no direct impact, like speed up on computational problems today. And this is my fourth slide, point 4. How did we get here? So I think it's valuable to give some kind of historical remarks. I think this may be useful to put quantum computing in context. There are many ways for technology to come into existence, right? Historically, we have seen all sorts of ways for quantum technology to come to be. Like ideas and their growth and adoption can have many different paths. Some ideas, for example, are solution driven. And there is a problem, and there is people that get together to try to figure out how to solve the problem. For example, I like to think of robotics like an area of this type, solution driven, right? Robots are built for specific purposes to solve specific problems. Quantum computing, when it was originally taught, was not really solution driven. It was more an emerging idea that came out from a landscape in the 80s, a landscape that included physicists exposed to the ideas of a notion of computer science. And here I have some technical terms like cellular automata or computer simulations. But what is important to keep in mind, the idea comes from physicists that are exposed to computer science. And in fact, the first people that thought about quantum computing were Richard Feynman, Nobel Prize physicist at Caltech, Yuri Manin, David Deutsch. And these are all people, were all people with a very strong physics intuition and an open mind. So quantum computing started to have its roots in the 80s, and then in the 90s, mid-90s, there was a turning point for quantum computing because Peter Shor at AT&T and Love Grover at Bell Labs, respectively, they discovered two pretty amazing algorithms. So the first one is for factoring integers, meaning one has a large number, want to find the prime numbers that multiply between them, give you that large number. And the other one is for searching databases, unstructured databases. And specifically, Peter Shor's result has fueled a lot of attention in quantum computing, since all suddenly, given the link between factored integers and cryptographic protocols, meaning protocols for securing information, suddenly quantum computers appeared like a future potential risk to some type of methods for securing information, specifically public key crypto systems of a certain type. And also in the 90s, the first proposal to build quantum computers came out. And somehow these areas were even a bit looked strangely from mainstream physicists at the time. And this was an area mostly part of academic an academic subject, and then it took a decade after to be consolidated. And finally, during the last 10 years, quantum computing slowly started to come out from academia, and they started receiving more financial support. And a number of national programs in quantum technologies, in quantum computing, have been launched during the last decade. See the UK, see the US, see China, see the European Union, Canada, and people started to be prototypes of quantum computers. Of course, these are mostly scientific experiments, but now there are definitely over 100 different research groups worldwide that are working on this topic, and in various aspects of quantum computing. By the way, so in Texas, there is a lot of excellent people doing quantum computing. And so you see, it's interesting that quantum computing, however, does not belong anymore just to academia, but there is a proliferation of organizations and startups that are contributing to its growth. And this is not just fascinating from the sociology of science perspective and sociology of science and technology perspective, but this really fuel innovation. And I'd like to go to my next slide. Oh, sorry, I mistakenly removed the presentation. Just a second, please. I'm going to get it back. Here we are. And this is my first slide. Point number 5, if you ask me, where are we now? From the scientific point of view, there's a lot of progress. People somehow use the term milestone maybe too often, but there is definitely a lot of progress. And interestingly, despite some deep and intelligent attempts to find theoretical roadblocks to the construction of quantum computers, there is no real reason why quantum computers cannot be built at scale. There is no real reason why innovation should stop. And these theoretical attempts to put roadblocks have to do, for example, with the idea that it's very difficult to control quantum systems, and that when quantum systems become large, then it's impossible to control them. But there are reasons to think that there is no roadblock at the moment for quantum computing. An important point is that it's really hard to build quantum computers at scale. This is something we should remember. So why? Because, as I said, quantum theory deals with atomic objects, small objects, and building a machine that can control such objects, it's very hard. It's hard because at atomic scale, matters behave in ways that are unpredictable. And I believe that, as I was saying, quantum computer has been very successful in establishing itself as a promising area of science. And you know, it's not just about building quantum computers, but it's also about designing algorithms for quantum computers. These are called quantum algorithms, procedures that can run on quantum computers. And if we go into the technological aspects of quantum computing, there are many ways that one can use potentially to build qubits, the fundamental blocks of quantum computers, to build quantum computers. Superconducting devices, light, atoms, ions, spins, when I say light, photons, and so on. And is there a winning strategy? There are some approaches that are ahead of others, but the road to scalable machines is still long, and it's unclear in the end if there will be a single winning approach, or even if new ones that we haven't seen yet will arise. But it's important to recall that quantum computers are naturally subject to errors that occur randomly during computation, and so building a machine that can correct errors is very important. So we need to protect machines from error, and this is something that is taking a lot of work, and it still will take time. So right now, the devices available out there are so-called the NISQ, where NISQ stands for noisy intermediate scale quantum. So these are machines, the NISQ machines are machines that cannot really correct errors. So the computation run is fragile, but they're very interesting machine they start to be at the cusp of what is called, in a technical term, quantum supremacy. And let me stress, this is a technical term. It indicates some computations, which possibly are not related to real world application, possibly useless with respect to applications, that can be run on quantum computers, but that would require too much time to be run on classical computers. So right now, there are no methods for error corrections on current machine. But what one can do is try to run the computer for the shortest possible amount of time, because error builds up with the hope to limit the amount of error. And for these reasons, algorithms that have a part running on a quantum computer and then another part sequentially running on a classical computers are interesting, potential candidate to show advantage in this NISQ phase. So these are called quantum classical algorithms. And it may be that these algorithms are indeed good candidates to show advantage in the NISQ phase before we will have error corrected machine. But you see, no matter you interpret quantum computers, quantum information processing, it's very interesting and should not be viewed as independent of complex IT infrastructure. Meaning that quantum classical algorithms are, yes, a reason to understand how to integrate quantum computers in the broader realm of computation of computers. But I think that there is a lot of value now to understand best ways to integrate quantum computers in IT environments that people routinely use today. And we should not consider quantum computers as isolated. Also, to learn as much as possible about what role a quantum computer could have in well-established computational pipelines, I think it's important to really understand how to integrate quantum computers in complex IT infrastructure. And surely, needless to say, that this is a smaller challenge than building scalable quantum computers. I would like to go to the next slide. Here is slide 6. Point 6, what is the impact of quantum computing today? I like to divide this slide into 3 areas. So first, society. Second, startups and enterprises, meaning people that are building stuff. And third, adopters, that is people that engage with the technology and use the technology. And somehow, even these are innovators in using the technology. For society, we witness now a number of investments worldwide. There are solid public investments. For example, during the last few years, various national initiatives have been launched. And at the core of these initiatives, usually there is establishing quantum centers of excellence or consortia, often including universities and companies. In other words, large collaborative grants. And you see, large collaborative grants can also be risky sometimes because they may not be necessarily focused on building technologies, but they're focused on scientific components. And in any case, I believe that at this stage, the scientific component of quantum computing is very, very important. So these investments are really necessary. Now, if you think about VC money, I believe that over $1 billion have been invested. I haven't seen the numbers recently, but it should be over $1 billion invested in 2021 in quantum computing. Many startups out there. So there are also accelerators right now, fully working with startups that develop quantum technologies. One, for example, is Duality in the Chicago area. They have a cohort of 6 startups every year that they support and coach, and I think this is fantastic. Now, there is startups, but also larger organizations. There are corporation enterprises that are building hardware application, and interestingly, many academics during the last 3 years have started companies, and maybe this is driven by the appetite of investor that is pushing the community to bring a realization of quantum computer closer, that invite people to realize their idea at a different pace and scale. But as a matter of fact, there are dozens now new startups in quantum computing that were funded very recently. Some of them build quantum computers with different technologies that usually are the technology that the academic founders are experts in, right? But then there are also some companies that work in the supply chain, like companies that build components, electronics, like cryogenic systems, lasers, and there are startups that build tools, portals like software as a service products, and these help customers approaching specific problems with quantum computers in specific areas of interest, like chemistry, for example. And then there's the group that I mentioned are adopters. So who are the users now? You ask me, who is using quantum computers? There's a number of enterprises that are running proof of concepts. What are they doing? They run proof of concept to see where the state of the art is, to see if quantum computers in the future will have a role with respect to their business. And example in the public domain are many that I can remember without really doing justice is Amgen, BMW, JP Morgan Chase, Goldman Sachs, is public information. And there are many examples in finance, biotech, oil and gas, material science, logistics. And these early adopters, what they do, they're preparing themselves for the future. And they have an active role, I think, because by playing, maybe the term playing is not great, by engaging in the use of quantum computers today, they contribute to innovate. And consider that indeed just using quantum computer today is somehow already innovating, because you need to massage problems to feed them to quantum computers. You need to understand different type of quantum computers and so on. And articulating use cases is so difficult. It's so difficult and so important. Now, in my next slide, I would like to tell you a little bit what is next, without risking of doing any futurology, because trying to determine the timeline of science and technology is clearly a difficult task, and one could venture into futurology, but in doing that, one would also risk of making wrong predictions, and I won't step into that. But technology starts from ideas, but then it requires somehow differently from science, in a way, a process for people to build a story around it, so that the technology becomes interesting and that is adopted, right? And right now, I think it's too early to talk about general adoption of quantum computer. And what we know really is that the timeline for having scalable quantum computers is far from being set. However, I believe that quantum computing is already contributing strongly in the way we do science, because, as I said previously, quantum computers should be interpreted as instruments for experimentation. And I feel that during the next years, we will see coming out many different types of quantum computers, often single-purpose machine, like built to solve some specific computational problems. For example, simulating some chemical reactions or some material science problem. And when it comes to applications, people talk a lot about three areas, right? Approaching problems that come from nature, problems that are more man-made, meaning related to processes, to business, and to production, and then there's machine learning. Now, there is substantial interest in quantum computing, for example, coming from financial companies that are exploring the possibility of using quantum computers for tasks like generating some complex probability distribution, like Monte Carlo algorithms, or optimization tasks like portfolio optimization. And these are tasks that are very time-consuming for computers. But when it comes, to machine learning, there are some interesting results out there, but it's still early to determine if quantum computers will be impactful in machine learning. However, since machine learning seems to be more and more an important area, pervasive really, I would expect that the interplay between quantum computing and machine learning will be very rich and will lead to interesting discoveries. And the challenge, of course, is to come up with new quantum algorithms. And the issue is that quantum computers seems to be very good in exploring mathematical structure like symmetry. The challenge is to identify such problems that quantum computers enjoy solving faster. And I don't think that in the last few years there's been enormous deep innovation with respect to this, but I wish to see more results that would try to dig deeply into the mathematics of quantum algorithms. And finally, a question that sometimes I hear is, will quantum computers replace our standard computers? And the short answer is no. I don't see why. Quantum computers will most probably be very specialized machine, and we already know from the theory that there are problems for which there is no point in using quantum computers. But definitely, I like the idea that one day quantum computers will be part of complex IT infrastructure, and we will work with quantum computers as we work with classical computers, side by side, and maybe we'll use some programming language that will be able to telescopically start from the very high level and then operate at lower levels down to the bare metals of quantum computers controlling the physics itself. This is, in the long run, it will be a serverless approach, right? Means user will be able to work in the same environment with any kind of hardware, which is CPU, GPUs, quantum processing unit, meaning quantum computer, and who knows what machine will be available one day. And of course, right now, programming quantum computers do not seem a major bottleneck. The bottleneck is really building devices, but also we shouldn't forget that it's going to be very important at some point to figure out how to program large quantum computers. And this brings me to the next slide. What are the challenges and the risks? Let's start with the challenges. You can build a quantum computer with 100 qubits, like so relatively large quantum computer or relatively small, depending if you're optimistic or pessimistic. These are large chips, and you can't shield them really accurately from noise if they become too big. So you need to make smaller chips and modularly connect them to other chips, unless you have some special design that is building directly in a single special chip. For example, there are some proposals out there of optical devices with 1 million qubits already printed on it, which is also very hard. But in general, you need to scale horizontally, and you need to plug these chips together in a way that can scale. And without modular approach, we will run out of steam at a few hundred qubits. And so meaning processors need to be connected, and one needs to test them independently to get the yield. Now, qubits that are at the edge of this processor, we need to talk to each other. And from the engineering point of view, this is very, very difficult. And there is no way to get to, let's say, 1,000 qubits unless people figure out how to connect smaller quantum computers. And I say because I say this because I hear experts out there talking about this topic, and surely we need better qubits, right? But this horizontal scalability seems to be very, very important. And let me stress again, it's difficult to articulate a useful application for quantum computers, and it would be amazing to figure out new application and to have this application available in the next future. Right? Design useful application could help, I believe, stimulating also innovation on the hardware side. Now, what are the risks associated with quantum computing today? I want to stress today. Let me say again, the term today, so the development of workforce is important. The field is highly fragmented, in this interdisciplinary, and in people with different points of view, different expertise. So we need to work on effective education programs to expose more people to quantum technology and science, undergrad, PhD courses, but also people working in industry. And another risk that I see is that whenever there are investments and the potential for investment, and obviously this is human nature, I suppose, there is a tendency to oversell. Like, we should avoid at all costs overselling quantum computing, because at some point it will be evident that people have actually, it will be evident that if there are false promises, at some point we're going to lose trust of the investors, and this is going to reflect negatively in the whole field, that could lose momentum and could affect negatively even academia. And we clearly don't want that. And then we want to avoid stagnation, indeed, due to maybe the fact that we are overselling quantum computing. Now, I like a quote by John Preskill, a quantum computing scientist, physicist at Caltech. So quantum technology is rife with accelerating opportunities, but surely many rousing surprises lie ahead, but the challenges we face are still formidable. This is something it's important to keep in mind. Challenges we face are still formidable. And we need to focus on the real challenges, not the superficial thing to gain attention. And ultimate risk is that one day when we have large-scale quantum computers, they won't be commercially viable. Okay, this is a risk in the future. I mean, I don't know, but it could be that it would be too expensive to run this machine, or that there will be so much advancement in classical computation that for certain practical purposes, classical computers will be good enough. But this is something we cannot tell yet. And quantum computing remains a deeply fascinating area. So my next slide is, and this is directed to you. Now, what can industry leaders do now? I know in the audience there are industry leaders, and this is a message to you. Now, quantum computing represents an opportunity, and like all opportunities, it raises questions, right? What does quantum computing mean for you? Where is the value for your organization, right? Here are 4 personas that I like: the quantum curious, the quantum pioneers, the quantum enablers, and the quantum opportunists. Where opportunist is a technical term here. And the question is, how does success look like for me as an industry leader? And the difference, and the answer depend on which of these personas I am, right? And the quantum curious want to learn, want to read, want to explore, they want to understand the state of the art of technology, and potentially they talk to their CTOs and say, look, please keep an eye on quantum computing. Then there are the quantum pioneers. These are the people that hire teams, that commit resources, that they engage the community, and they sponsor research in academia, for example, and they try to push the field itself. And the quantum pioneers are innovating directly. Now, in this group, there are the hardware builders, for example, and another group that I think is very important is the quantum enablers, like startup system integrators, educators. They're in the higher level of the stack, right? They built on quantum and help grow in awareness around quantum. And finally, the last persona is quantum opportunists. So these are organizations that don't really care about quantum computing as a field, but care that quantum computing is going to solve problems that they need to solve. So in other words, it could be quantum or a classical computer as far as the problem is solved. And the quantum opportunists are then technology agnostic and usually decide to sit and look and wait for technology to evolve, or in other cases, they work together with professional services, like consulting businesses, or with the quantum enablers to figure out if and when quantum computing will impact their business so that they can be ready in the case quantum computing is successful, which is also something that quantum curious do, right? And I'm going towards the end of my presentation. Would like to leave some time for questions. Point 10, where can I get started? So I hope I stimulated your imagination and your interest with this talk. And I guess depending on which of the previous groups you are, that's you need to ask yourself. So am I a quantum curious, a quantum enabler, a quantum pioneer, or a quantum opportunist, right? You may decide to engage with the technology depending on the group. So if you want to learn a bit about quantum computing, I suggest you to read a lovely piece of text on the internet titled Quantum Computing for the Very Curious. So this is extremely clear and it does not require strong mathematical literacy. And one of the authors is Michael Nielsen, which is a pioneer in the field of quantum computing. The second link here is a US Government Accountability Office report. And the report assesses the potential of quantum technologies, quantum computing, benefits and risks, and policy options that could help foster their development. And it's an interesting report. And finally, and this is the third link, if you want to get your hands dirty, Amazon Bracket, and notice here, no C, this is a technical term in quantum physics. It's for geeks, right? Amazon Bracket is an AWS service and it's a cloud service that gives access to quantum computers built with different technologies. It's pay-as-you-go, it can be accessed by anyone. And the goal of Amazon Bracket, despite it's so early for quantum computers, is to give a window over an evolving technology. And it's open, it helps catalyzing R&D in quantum computing. And there is a number of quantum enablers and like startups that are building application for quantum computing using this service. Rod, if I have an extra minute, I have a final slide. Otherwise, I'm happy to stop here. You please, you decide.
Yeah, thanks, Simone. We do have some questions, and I'd really like to encourage anyone else to go ahead and submit some more questions. Simone, I'm gonna kind of start with some of these. And first of all, you explained quantum. I mean, I wish I would have had you as my quantum mechanics instructor at Penn State when I was a physics major, because I learned things that I wish I would have known at the beginning of the class that you were able to communicate very clearly in just a little bit. So thank you for your expertise and being able to, to be able to bring a very complicated type of technology to us in a way that hopefully most of us could understand. So companies seem to be engaged. By the way, people that have submitted questions, I've tried to summarize them as the talk went on, and as some of those questions were answered, I tried to summarize them and maybe update them a little bit based on Simone's comments after you submitted your question. So it seems as though there are a fair amount of companies that are already engaged in this. What does the technology look like? Are there specific prototype challenges that that those companies are engaging? So, for example, of course, Amazon, you've got 3 major efforts going on. You mentioned BMW, Goldman Sachs. How are they physically engaged in building quantum computers?
So rather than building quantum computers, they use quantum computers and they innovate in quantum computing. They try to understand what are use cases that can potentially impact their business. So at this stage, they innovate by building the state of the art of applications, trying to determine what quantum computers can really do for their business, and trying to determine if, as I mentioned during the talk, if and when a quantum computer can impact their business, and they prepare for that. And one important point is that there are organizations doing, for example, analysis of resources, like how large a quantum computer should be to impact my business. Or suppose that there is a quantum computer of this size, what can I run on that quantum computer? What can I do? Can that quantum computer really be useful for production workloads? These are questions that a number of organizations are asking at the moment out there.
Yeah, excellent. It is, as you just commented on, a nascent technology, trying to get support and funding. Nan from Red Hat asked a great question. If it's really hard to justify businesses' benefit right now, how did you get this started at AWS? How did you get so much support? You've got a team, you've got facilities, same for the other companies that you mentioned. How can you justify and get that kind of engagement and funding support?
Yeah, so there are 2 points here that I think are important. First, we need to have long-term vision. So quantum computers are going to be deeply impactful. They are going to be very important. As I said, they're important in science. They're going to be important in industry. So we need to have long-term vision. Now, you see, everything we do at AWS starts from customers. And there was a strong signal coming from customers that wanted to engage with technology, wanted to understand what is real and what is not about technology, wanted to start, I use the term, making your hands dirty by working with quantum computers. And in fact, one of the things we have built, which is Amazon Braket, the service that gives access to quantum computers, does exactly that, gives a window over an evolving technology, and customers can themselves determine where the state of the art of technology is, and they can prepare for the future. And of course, they can already innovate and contribute to the field itself.
Yeah, excellent. You mentioned a couple of applications, high level. Jacques Camier from Autumn 8 asked, are there specific applications? Are there some user cases where you can say let's pick on Amazon, that you've actually had some experiences and some run-throughs?
Yeah, you see, in one of the slides, I proposed a distinction between 2 families of applications: the application that have to do with nature and applications that have to do more with business and processes and people. Now, if you look at what the scientific community, and the community industry believes, believes about the current state of the art in quantum computing, possibly the first applications where quantum computers will be impactful, of course, apart from scientific application and learning more about nature and quantum computers themselves, by the way, will have to do with this family of applications that are related to nature, like simulating physics. It's very time consuming. It takes a lot of computational power to simulate certain chemical reactions, for example, if a chemical reaction engineer, or modeling some configuration of matter, like modeling materials. So it is expected that some of these more nature-related applications are going to come sooner than applications that, for example, have to do with logistics. But there is innovation happening across the board as we speak. This is a very fast field, and I really, really hope that there will be innovation that will impact application in every aspect of business.
Yeah, excellent. A series of questions kind of go around this theme, Simone. How do you defend against the bad guys? This might have been one of the myths that were in your first slide, but it was missing there. But clearly, this is a technology that could allow bad guys to be able to get in, to be able to do things, be faster, and so on. Any comments?
Yeah, so there are very accurate reports about this subject out there. So here, I think that the most important thing to keep in mind is the following. So first, the timeline of quantum computers is uncertain. And for a quantum computer to be a threat for information security, one will need a large quantum computers. We are talking about millions of qubits, right? And right now we have computers at a few dozens of qubits or around hundreds or so. So meaning the timeline to get there, it's uncertain, but this does not diminish the importance that we should take care about that future. You know, there is often a conversation out there, discussion about this idea of data harvesting, like get data today that you cannot decrypt, then one day, even if it's a deep future, maybe 20 years from now, maybe you can decrypt this data with a quantum computer that will be available. So what one should do and can do is to start thinking about protecting this data even for the deep future. Of course, if you believe that this data needs to be kept protected in the deep future. And there are ways to do that. There is post-quantum cryptography. These are classical algorithms, classical protocols that are conjectured to be safe against quantum computers. There is lots of work around this topic, scientific works in academia, in industry. There are proposals at NIST about post-quantum cryptography. And another option is also quantum cryptography, which is using certain properties of quantum systems for securing information. So in summary, nobody knows what is the timeline for quantum computers to be a threat to public key crypto systems. It could be conjecturally and plausibly deep in the future because we need, because for these large quantum computers with millions of qubits will be needed. But of course, there are methods to protect information against these, and these methods are either post-quantum cryptography. Apologies. Post-quantum cryptography or quantum cryptography. Sorry, these terms are very similar to each other, but they mean two very different things. One is about classical algorithms to protect against quantum attacks, classical protocols that are safe against quantum attacks, and the other one is protocols that use quantum information itself.
Yeah, great. Last question is, how do you get the workforce of tomorrow to really be engaging in this new technology development? So I'm going to give you a really loaded question. First of all, why would anyone look at this pretty risky business as a career maybe to pursue? Secondly, how do you motivate and inspire, elementary school kids to seniors in high school to embrace quantum computing? And then finally, if they do and they go to college, what kind of classes, you just don't right now see quantum computing 101 out there just yet. What kind of classes do they need to take? What kind of majors would you recommend, at least for the near term?
So quantum computing is an exquisitely interdisciplinary area, right? And many people with many different skills could contribute to quantum computers. when I did my PhD, by the way, I have an undergrad degree in philosophy. So I ended up to do something which doesn't seem to be particularly close to philosophy. But you see, one needs to be curious, right? Curiosity is what drives interest in things, and quantum computing is deeply fascinating in many different ways, from the scientific perspective, from the technological perspective. Now, as I said, being a very interdisciplinary field, there is a space and need for people that have different skills. Mathematicians, engineers, material scientists, physicists, computer scientists, and so on. And since it's still very early, I think it's an amazing opportunity to work in quantum computing, because we will see lots of innovation and lots of evolution on this space. So, I mean, I love this field, right? So obviously, I'm very much biased when I talk about quantum computing. But I don't see it as a risk for someone that wants to study quantum computing. I see it as an amazing opportunity and as a new branch of science and as a new branch of technology. And I don't think that it requires a very, very technical skill. It's not like, I don't know, being a brain surgeon, right? So if doing brain surgery is something very, very specific, right? Quantum computing is a very broad, very interdisciplinary.
Yeah, very interesting. I don't know, Simone, it sounds like brain surgery to me, and I'm a physics guy. So thank you. Very well done. Thanks to all of you for your questions today. First of all, I want to, again, thanks Simone, but just really an interesting topic. I made a comment in the chat room, Simone, while you were chatting about, we probably won't have quantum computing laptops. Who knows, man? Once you get this thing moving, I remember the quote that the IBM CEO back in the 40s said when he launched his fifth major computer. How many computers will we have? And his answer was 6. I've got 6 in my attic right now. So who knows where quantum computing may go? And it's just really thrilled to hear your insight at the very beginning of this frontier. I want to also welcome Wolters Kluwer today. They are a new member company to the Tech Titans. If you would like to learn more about the benefits of membership, please reach out to Paul. Paul will connect you to the membership folks and get you some more information, and you can see the kind of benefits and engagement. Tech Titans does an amazing service to not only the high-tech companies in the Richardson and North Texas area, but also all the surrounding community with their K-12 outreaches, their lobbying, and so on. So great organization. Once again, Simone, thank you very much. An outstanding presentation, very complex topic. I think we're all much more informed about what's going on, and I think we all need to open up our new branch in all of our organizations on computing, quantum computing, so we can get this moving. On behalf of Tech Titans, thanks once again to UT Design for being the Tech Titan Tech Industry Luncheon presenting sponsor. Please make sure to reach out to Don or Cynthia if you've got any questions. And again, we look forward to seeing everyone at the February 18th Tech Industry Luncheon Salute to Black History Month. If there are no other things, Paul and Mallory, I will just say that we are adjourned. So thank you very much, Simone, rockstar. We appreciate you, man.
Thank you. Thank you for your attention and for listening to my talk. Thank you.
Oh, actually, somebody did make a really good point. If you've got any questions for Simone, he did give an email address. Let me see if I can pull that up, and I'll put that in the chat. I'm going to see if I can read my very bad handwriting. So I'll put that in, and that way you guys can see it if you can still stay on for just a little bit. Oh, Simone, can you do that? Because you're probably much better at your email address than I am. Thanks very much.
Just done it.
All right. Simone, what a delight. Be safe. Take care of your baby girl, and have a great weekend.
And you. Thank you.